Good morning, students. Let's start a new class on rotation plus translation. So in yesterday's class what we learned, how to write speed, velocity, distance, displacement and acceleration also. But acceleration again I am going to revise. Okay, and then after that we will see momentum, kinetic energy and angular momentum out, right? Because these are all the basic things in this one. If you know how to write it, that means any question which is given to you based on this can be done easily. Okay, so acceleration, what I told you, acceleration in combined translation plus rotation, right? So what it was, we said that if suppose we are talking only about translation, then there is acceleration like this for every particle. Acceleration will be in this way, right? Here also. This is only for translation. When you talk about rotation, in rotation means we are talking about a circular motion, and in circular motion we have two accelerations. What is those? Tangential and radial acceleration. So any particle over here, okay, suppose this one here, so it is having tangential acceleration like this and radial acceleration which is omega square r. Tangential acceleration used to be what? R alpha. Okay, this is omega square r, that is AR, right? Particle over here, if suppose it's moving like this, so AT, and in this direction radial acceleration. The particle over here, AT, and radial acceleration inside, and the particle over here, this is AT, and this is radial acceleration. Okay, so total acceleration is what? This plus this. That means total acceleration will be AT plus AR, there is a vector relation between them also, plus A, which you can say ACM. The ACM, acceleration of center of mass. So this is the total acceleration in translation plus rotation. And we saw that yesterday. So no doubt about that. Okay, so this is the way to write. Okay, we can solve. If you want to solve any question also, we can solve on that one. Okay, we can frame a question. We can frame one question and we can write. Okay, so what type of questions we can frame? Simple question. If I try to frame in this one, suppose acceleration is 2 meters per second square. Okay, let's say the alpha. Okay, alpha is okay, that also 2 radian per second square. Radius is 1 meter only. Take it 1 meter or half a meter we take. Right, and at any instant, now instant we have to take. Okay, because in radial acceleration, omega is involved. So we need to have an instant. Okay, so at, let's say some t equal to 2 seconds, omega value is 4 radian per second. Find total acceleration. Find total acceleration at t equal to 2 seconds. That means at this instant only. Now how to do it? What is total acceleration? Total acceleration we know it is AT plus AR plus ACM, right? Now AT, what is AT? AT is R alpha. For which particle we are finding? That is also important for us, right? That is also important for us. So let's say this point V it is. For this point we are finding this point V. Okay, so AT is what? R alpha. So R is half, alpha is 2. So R alpha means 1. Which direction? This direction is AT. then omega square r, where is omega square r? In this direction. So AT value is 1, okay? 1 meter per second square. This is omega square r. What is omega? Omega is 4. Omega square 16 into r 1 by 2, 16 by 2, 8. So 8 is acting in this direction. Resultant we can find becoming somewhere here. So what I am going to do in this part, I am going to write it this way. Okay, AT, I am writing it as I cap. Okay, omega square r minus 8j cap. Okay, plus ACM 2I cap. So basically the acceleration is 3I cap minus 8j cap. So if I want to find its magnitude, I know what to do. 3 square plus 8 square. Okay, 64 plus 9, 70. This will be the resultant acceleration. What will be the direction? That also we can find from here because we have the vector form. So that's simple. Okay, depending on the values, we can find its direction also. Okay, this is how acceleration can be written. Now let's go on to momentum. Okay, we all know that momentum, when we discussed in the last chapter, center of mass, we discussed that it is basically mass into velocity of center of mass. Yes or no? Absolutely. And nothing has changed. Even in translation plus rotation, it is mass into velocity of center of mass. Okay? Exactly same, no change. There is a derivation for that, but I am not going into derivation. Momentum object due to combining translation plus rotation. Okay. So I was saying that I am not going into derivation of momentum, kinetic energy and angular momentum. It's not necessary to go for the derivation and derive the formula. But rather it's important for us what it is, understanding it and then use it. That's more important. Okay. So when we say momentum of object, as I told you that we already know momentum is what? Momentum is basically mass into velocity of center of mass. We know that. So same thing is here also. Suppose that this is the object. Okay. Let's say it's moving with 10 meter per second. And at the same time, it's rotating. It's rotating with 5 radian per second. And I ask you, what is the momentum of this object? And its mass, maybe 2 kg. So its momentum is mass into velocity of center of mass. That means 20 kg meter per second. 20 kg meter per second. So does it mean that there is no impact of with what energy it is rotating? Yes. There is no impact of rotation on momentum. Momentum will remain mass into velocity of center of mass. So, okay. But if suppose that something like this is happening, the same body, let's say now we are moving it like this, and here this is 10 radian per second. Same 2 kg. Now momentum is what? I would say, what is the velocity of center of mass? 10. Here what it was, 10. What you have changed? Omega. So omega has no effect on linear momentum of the object. It is still 2 into 10 I cap. That is 20 I cap kg meter per second. There is hardly any change. If you have changed omega, you have decreased omega, you change the direction of omega. Maybe this is 10 meter per second, this is 2 kg, and now it's moving like this with 2 radian per second. What is the momentum? Still momentum is same. 20 I cap kg meter per second. Understood that? It has only concern about velocity of center of mass and nothing else. Okay, that's momentum. Translation plus rotation. Right? Okay? Right. Now, let's go for kinetic energy. Okay? What is kinetic energy? Kinetic energy of translation plus rotation. Right? So object is again you can take even rod also. Okay, there's nothing like we have to take only wheel. You can take rod also, or you can take wheel also. There's nothing in it. So VCM and then there is omega also, because both are happening. Or if you want to take a wheel also, the same thing. VCM and here is omega. Now, as I told you that whenever we talk about translation and rotation, we have to break it into two parts. One, motion of center of mass, and then motion of body about center of mass. And we discussed that motion of body about center of mass is circular motion. Right? Our entire body is rotating. It's a rigid body. It's not a single particle that I can say that it's a circular motion of single particle. Entire body is rotating about the center of mass. So here we have to write kinetic energy. Whenever we talk about kinetic energy, then here also we will be dividing it into two parts or breaking it into two parts. Kinetic energy of linear motion and kinetic energy of rotatory motion about center of mass. Okay? Because there are two motions actually. Linear motion is also there and rotatory motion is also there. So how to write it? We'll say that it is basically kinetic energy of linear motion, that is translation, plus kinetic energy of rotation, that is kinetic energy. Here also derivation is there, but I am not going into that derivation. That's unnecessary basically, that's nothing else, because we know what it is basically. So kinetic energy of translation, what I write? So when you are going to talk about translation, you are going to consider this as a particle where entire mass is concentrated. Okay, where entire mass is concentrated. So we are going to write half m total mass into VCM square. Because when you talk about translatory motion, only one particle is there which is moving in translatory motion actually. Because remaining all are doing circular motion. Only one particle, which is the center of mass, that only will be moving in straight line path. And that's why half m VCM square. Right? Then kinetic energy of rotation plus half ICM into omega square. Now these are important for us. You have to remember half m VCM square plus half ICM omega square. These are very, very necessary for us to remember. If we are going to forget it, suppose that we are going a problem in which you are conserving angular momentum and then you have to write kinetic energy. You conserve angular momentum about some other axis. Then you have written kinetic energy also about that axis. That will not work. Kinetic energy in this one we have to write half m VCM square plus half ICM omega square. Then only it's going to work. Okay? Clear? That's your kinetic energy. Now, next one, I'm going for angular momentum. Angular momentum. Okay. So, angular momentum. Right? Angular momentum of object due to combined translation plus rotation. Okay. Let's take a rod over here. Okay. This is VCM and this is omega. Right, length is L. Now suppose we want to write angular momentum at this point. This point is A. Okay, about this point I want to write it. So what is the first thing? Now we know that there is one particle which is doing linear motion. So we are going to write mvr or r cross mv for that particular particle which is doing linear motion. Remaining all the body, what it is doing? It's doing circular motion about center of mass. Then that one we will write in the form of I omega. Okay. So here also again break. What break? Break it into translatory motion and rotatory motion. So translatory motion for center of mass. But first of all, let's join. Say this is R. Okay. So first I am writing total angular momentum about A. First due to linear motion. What is it? R cross M VCM. Due to translation. Then plus ICM into omega. Plus ICM into omega. Okay. R cross MVCM plus ICM omega. Again, very similar thing. But we need to remember that that's really necessary for us. Okay. So this is how angular momentum is written. I'll give you some questions. We'll see that how to write angular momentum in particular. Okay. And this is the formula. Now let's see. Now suppose same rod only I am taking. Okay, this is moving, let's say at 5 meters per second. Mass is 2 kg. Okay. Omega anything you can take. 4 radian per second. Its length 2 meter. Okay, and a particle. Okay, take point A only. Point A is here. Okay, about point A you have to find it, and this is given to you 1 meter or half meter. Okay, we have to find angular momentum of this. Right? How to do? Join this first because this is R for you. And let's write what is the formula. L equal to R cross MVCM plus ICM into omega. Right? Now let's see. R cross MVCM. Now we know that this angular momentum means is MV perpendicular R, right? Or R perpendicular MV. So MV is in this direction. Perpendicular component of R means this. Perpendicular to what? MV only. Right? So this. How much is this? This is 1 meter. Which direction is our angular momentum? That also we should. R cross MV. Inside. So how much is coming? 5 into 2, 10. 10 into 1. R, this is R perpendicular, okay? Are you able to understand? Perpendicular. So 5 into 2 into 1, that is 10. But which direction it is? Minus K. Inside it is. Okay. Then I omega. What is I? I will be ml square by 12 here. So plus m is 2. L square means 2 square by 12 into omega. Omega is given 4. Let's check the direction. Why? Because we have to add or subtract, we don't know. Which direction is rotation? Inside. So angular momentum is inside. Rotation is clockwise, angular momentum inside. So this is also minus K. Okay, so what are we getting here? This is 4, this is 3. So this is 8 by 3. 8 by 3 plus 10. I think 38 by 3. Minus 3. Okay, this will be angular momentum. One more question. One more question we'll try. Okay, now in this question, again rod only. Suppose this rod is of length 4 meter. Okay, velocity of center of mass, let's say 10 meter per second. Okay, angular velocity omega 5 radian per second. Okay, and you have to find angular momentum about this point here. This point. So this point is A. And this distance from the center is 1 meter. Okay, and this distance, anything you can take, 3 meter. Okay, we have to find angular momentum. What to do? Formula we know already. L equal to R cross MVCM plus I omega. Again, MVCM into what? Perpendicular R, which is perpendicular to MV. So perpendicular to MV is in this direction. A is here. So perpendicular distance is what? This only. This is perpendicular. How much is this? This is 4. This is 2. This is 1. It's given actually. It's 1 meter. So that's 1. M into B means it's mass. Mass I have not given you. Mass you take as 3 kg. Okay. So 3 into 10, 30. Into 1, 30 only. 30. But which direction? This is R. This is R actually. R is like this. So R is this way, MV, inside. Okay, and that's inside minus K cap plus I omega. What is I? ml square by 12 again. M is 3. L is 4 square by 12 into omega. Omega is 5. Now let's talk about direction here. Which direction it is? Rotation is anti-clockwise. That means angular momentum is outside towards you. So that means K. K cap. 3 into 4, 12. So this is cancelled. This is 20. This is 30. The answer is 10 minus K cap. 10 minus K cap. That's the angular momentum. Right? Okay. This is how angular momentum is written. Okay. Kinetic energy also, now you know that once you can write angular momentum, you can write kinetic energy also. There is no problem with it. Right? So then, next, I am going to solve problem. Okay, problems based on that. But first, let's see that what we have done. We have learned how to write every parameter for combined translation and rotation. Every parameter, distance, displacement, speed, velocity, linear momentum, acceleration, kinetic energy, and angular momentum. So most of the things will be based on this one. So it will be easy for us to write it. Right. So what I am doing now, what kind of questions we are going to attempt? The question that I am going to attempt is the similar question that we did last, before going for this transmission and rotation. What was the last type of question? Rod is hanging. Okay, and one bullet is coming and striking. Same questions, but this time around, rod is not hanging. It's free. Free to move. Here is the rod. Okay. Shall we take value or without value shall we do first? First we'll do without value, and then after that we'll take the value and we'll see that. Okay. So let's say this rod is having mass m, length is L. Okay. And bullet is coming. Let's say it's striking from here. coming with velocity v naught, and this is at rest. Everything is horizontal, okay? Horizontal plane. Horizontal plane. Horizontal frictionless, okay? Horizontal plane and smooth surface. So no friction. Okay? Just a minute. Okay, so horizontal plane is there, smooth surface is there, rod's mass is there, length is L. A bullet of small m with velocity v naught is coming and striking it. Coefficient of restitution is E. Okay? If they are giving elastic collision or whatever, we know that what is coefficient of restitution, right? We can take it. Right. Now, when this bullet is going to strike this one, do you feel that it is going to have angular velocity omega? Will it rotate? Answer is yes. It will rotate. Will it move? Translatory motion also will be there? Answer is yes. Because this is going to impart translatory motion also, and this is going to impart angular motion also. Both will be there. Okay. Now, the thing is, first of all, is the momentum conserved? Because when the rod was hanging, at that time I asked you whether the momentum is conserved or not. You said no. Why it was not conserved? Because there were forces due to hinge. Okay, forces due to hinge were there. That's why momentum was not conserved. Let me make it. It's like this. Okay, this bullet strike over here. So what happens is when it strikes, you know that here normal force is acting. Impulse you can say, and on this one also this impulse was acting. So net force here is 0, but because of the hinge there were forces, so we could not conserve momentum. But in this case it's not hinged, and this bullet is going to strike over here. On the bullet there is normal impulse like this, and on the rod there is normal impulse like this. So if you ask about the net force, that is 0. Can we conserve momentum? The answer is yes. We will conserve momentum. Okay. So momentum conservation means we have to go back to how we return momentum of translation plus rotation. Right? So we are doing it. Momentum is conserved. Momentum is conserved. Said okay. Momentum before collision. Momentum before collision you are writing, that is mv naught. Momentum after collision. After collision, let's assume this one. Okay, let me make it over here. After collision, I am considering this is moving with v. Okay, and at the same time started rotating like this with omega. Okay, and this bullet, let's say this bullet here is having velocity v1. Okay, we have assumed it. So how many unknowns are there? V is unknown, omega is unknown, v1 is unknown. 3 unknowns are there. We have to find all 3 values. So how many minimum equations we require? 3 equations we require. Right? Okay, let's frame. So first equation I am trying to frame in this one, conservation of momentum I am doing. Initial momentum mv naught, final momentum. Final momentum of this one also is there, mv1, let's write for bullet. Plus, now I have to write momentum of this one. Angular velocity is omega. What will be momentum of this rod? Mass into velocity of center of mass. That's all. Whose mass? Rod's mass. Rod's mass is capital M. So M into V. Finish. Equate both. Pi equal to Pf. So mv naught equal to mv1 plus mv. They are all in same direction. V naught, V1, V, everything is in same direction, so no problem. Okay. Then what you can do? You can write angular momentum. Angular momentum also is conserved. About which axis? In the case of hinge rod, we could conserve only about the point of hinge. Right, because the torque about that point only was 0. Because hinge were acting at those points. The forces due to hinge were at that point only. So torque due to those forces was 0 at that point. And torque due to these two, N here, normal impulse, was also 0. Right or not? Because net force itself is 0 because normal impulse. So torque also was 0 because of that. So only at hinge point it was 0. We discussed that also. Okay, shall I do it over here again? Sit. Okay, to bullet you give normal impulse like this, and to rod normal impulses like this. So torque about this point of this end and torque about that point because of this end. 0 only. Yes or no? Because of this outside, because of this inside. So torque is 0 because of these two. And hinges are acting over here, the force is due to hinge. So their torque is 0 only about this point. Any other point if you take, there will be torque because of these two, N1 and N2. That's why angular momentum was conserved in this case only about point of suspension. Here what to do? Is there any point where angular momentum is conserved? Now in this case you see, there is net force 0. So if net force is 0, you can conserve angular momentum wherever you want, because torque at every point is 0. That's what we discussed when we were discussing torque, when we were discussing equilibrium, if you remember that. If the net force is 0, okay, then you can take torque about any point, the torque will be 0 only. So if torque about any point is 0, you can conserve angular momentum anywhere. Anywhere you can conserve angular momentum. Your wish. Okay. So normally if you see in the books, they will conserve it about center of mass. Okay. Maximum books will say center of mass. Or there is another point you can find. What is that point? That point is somewhere here, along this line of collision. Along the line of collision will be there, where they will be conserving angular momentum. Or they will be saying torque about this is 0. Okay, so it's our wish where we want to take conservation of angular momentum. Okay, so doing that, conservation of angular momentum now. Conservation of angular momentum. Okay, initial angular momentum. About which point I am taking? Let's say we will take about this point only, A. Okay. Now initial angular momentum, who's moving? This is moving. Here is somewhere point A. Okay. You have taken it over here. Okay. So initially who's moving? This. What is its angular momentum about this point? They are in the same line. This is R and this is angular. 0. Final angular momentum. Now final angular momentum is with bullet as well as with rod. So bullet again, we are again in same line. For bullet again 0. For rod, angular momentum. There is I omega, no doubt about that. And there is MVR also, you see that. This is R. Correct? So in which direction is that? Inside. Okay. What is this R value? R value perpendicular. Is this, how much is the length? L. So this is L by 2. So capital M, V, L by 2. But direction only I have to check. M, V, L by 2. What is the direction? We said inside. So minus K you want. Minus K you Okay, then what? ICM omega. ICM is what? ml square by 12. ml square by 12 into omega. Omega is omega. Omega. What direction? You can see that it's anti-clockwise. It's towards you. That means positively. Equate both. We got another equation. You see that? When we are equating both, this will be equal to this. One is negative, one is positive. So we can write as m v l by 2 equal to ml square by 12 into omega. This is my second equation. This is second equation. Third equation, coefficient of restitution is given for us for that, right? So coefficient of restitution we are going to use. Where here I use. Okay. Coefficient of restitution is what? Velocity of separation by velocity of approach. Which point we are going to write coefficient of restitution? At the point of impact. At the point of impact. So coefficient of restitution E equal to velocity of separation by velocity of approach. The velocity of separation, how you see that? At this point. Right. Velocity of approach we already know. Velocity of approach is V0, so there is no problem. You can write over here V0. Velocity of this point of the rod. This point of the rod is this point, because of rotation, if you see, this point's velocity is omega L by 2. Omega L by 2. Because this is L by 2 radius. This point's velocity is R omega. So L by 2 omega plus V, because of translation. L by 2 omega plus V, this point's velocity, and this bullet is having velocity V1. So velocity of separation is what? This minus this. L by 2 omega plus V minus V1. Are you able to understand that? L by 2 omega plus V minus V1 by V0. Right? That's it. 3 equations. 1, 2, 3. Whatever we want, we can find it without any problem. Now they can give, anyways, this is striking, okay. They may give that this bullet is coming with an angle. Let it come with an angle. We know that what we have to take. Right? Because we know that the component that is coming, only we have to take this component. Right, this sine component. And then we have to do the same way. Because V cos theta will remain same. There is no problem in that. So we have to solve it in this way only. Correct? So this way, conservation of angular momentum you can apply. More questions we'll do that in the next class. Okay? Alright dear, bye bye.